Large language models are incredibly powerful, we know that, but they also need just a massive amount of compute power.
Makes them tricky to deploy, right?
It's a real bottleneck. And one key way to tackle this is quantization, basically reducing the numerical precision.
Making the model smaller and faster that way.
Yeah, less data per number,
Yeah.
essentially.
Okay, and there are a couple of main ways to do this. I think post-training quantization and quantization-aware training. What's the difference that matters for us here?
So post-training, or PTQ, you do it after the model's trained.
Hmm.
It works okay for, say, 8-bit precision.
Okay,
But if you push it further, like down to 4-bit, the accuracy can really take a hit.
right.
Quantization-aware training, or QAT, builds the quantization into the training process itself.
Ah, so the model learns with the low precision constraint.
It adapts.
Yeah.
And that's crucial for getting good performance at really low precisions like W4A4 4-bit weights and 4-bit activations.
Got it. So this deep dive is really about understanding how that QAT behaves, specifically at this ultra-low W4A4 level. Yeah, because, we have these scaling laws for regular full precision models, how they improve with size and data.
Sure, those are pretty well established.
But for QAT, especially W4A4 QAT, understanding how the quantization error itself scales wasn't as clear. How does model size or data volume affect that error?
And that lack of understanding makes it harder to design these efficient quantized models effectively.
Exactly. So we're looking at this paper, Scaling Law for Quantization-Aware Training, to get some clarity.
Okay, so what's the core question we're trying to unpack from this research?
The main goal here is to pull out the key insights on how that W4A4 quantization error is affected by, well, three main things: model size, the amount of training data, and also the quantization granularity, how finely you apply the quantization.
All right, let's get into it then. This new unified scaling law they propose. What's different about it?
Well, earlier attempts often just focused on model size, maybe data. This new one explicitly brings in model size, N, the number of training tokens, D, and this granularity factor, G.
Granularity, G.
Yeah.
What does that represent exactly?
It's about the size of the block of numbers you quantize together. Finer granularity means smaller blocks.
Okay, and they put this into a formula.
They did. It looks like this. T NDD, to the power of GOD, log base 2 of G to the power of GOD, all divided by N to the power of GOD.
Whoa, okay, so Gobi is the quantization error.
Yep. And K and those gammas are just parameters they fitted from their experiments.
So N, D, and G all playing a role. What did they find when they tested this? They ran a lot of experiments, right?
Yeah, 268 QAT experiments. Quite comprehensive, and they found some clear trends. First, the W4A4 error, W4A4, it went down as model size N got bigger.
That makes sense. Bigger models have more capacity to handle the approximation.
Seems like it. They saw about a 34% average decrease when going from a 74 million parameter model up to nearly 600 million.
Okay. What about the training data, D? More data is usually better, right?
Well, interestingly, not for the quantization error itself. They found W4A4 actually increased as the number of training tokens D grew.
Really? That's counterintuitive.
Yeah, it went up by an average of 22% when they increased data from 10 billion to 100 billion tokens.
So just throwing more data at a QAT model might actually increase the specific error from quantization.
That's what their results suggest. The paper hints that maybe more training makes the internal activation distributions more complex, harder to quantize accurately to 4 bits.
Huh. Okay, something to keep in mind. What about the last piece, granularity, G?
For G, they found that finer granularity, smaller quantization groups led to lower error.
Okay, so more detailed quantization helped.
Right. There was a clear difference in error between the coarsest and finest settings they tested. Think of it like using more precise measurements.
They visualized this too, I think, in Figure 1.
Yes, Figure 1 shows these contour plots. You can see how the error level changes depending on N and D, and they have separate plots for different granularities, G. It really shows the interplay.
And did their formula actually predict these results well?
Very well, it seems. Figure 5 compares their law's predictions against the actual measured errors. They reported an R-squared value of 0.944, which is a very strong fit.
Okay, so the overall law seems solid. Then they went deeper, looking at weight versus activation errors separately. Why do that?
Yeah, to understand where the error is coming from more specifically, is it mostly the weights being quantized or the activations?
How did they isolate that?
They trained models where only weights were 4-bit, W4A16, activations at 16-bit, and others where only activations were 4-bit, W16A4.
Clever. And what did that decomposition show?
A really key finding was that the total W4A4 error was very closely approximated by just adding the weight error, or W4A16, and the activation error, W16A4.
So you can pretty much just sum the parts to get the whole error.
Looks like it. It means analyzing them separately gives you a good picture of the total error.
Okay. And how do these separate errors behave with N, D, and G? Were they the same?
Similar overall trends, but with different sensitivities. For instance, weight error W4A16 decreased faster with bigger models N than activation error W16A4 did. But weight error W4A16 increased faster with more training data D than activation error W16A4.
Interesting. And granularity?
Activation error W16A4 was much more sensitive to the granularity G than weight error W4A16 was.
Figure 7 shows these differences visually.
It does. You can see the different slopes and responses clearly in those plots for W4A16 and W16A4 against N, D, and G.
And they compared the size of these errors directly using a ratio, R.
Yes, R is just W16A4 divided by W4A16. They looked at this in figure 8A. The consistent result was that R was generally greater than 1.
Meaning activation error was usually larger than weight error for W4A4.
Typically, yes. That was the trend.
But it wasn't always the same amount larger. The ratio changed.
Correct. R tended to get smaller as the data-to-model size ratio, DN, increased. So more data relative to size seemed to make weight error a bigger part of the total. And R got larger with coarser granularity, G, again showing activation quantization is more sensitive there.
So a big takeaway seems to be that activations are like the main hurdle for W4A4 QAT.
That appears to be the case based on this analysis. Activation quantization generally contributes more to the error. Improving that seems critical.
And the paper digs into why activations are harder. Something about outliers.
Activations in LLMs can have these extreme values, outliers, that are just really hard to represent accurately with only 4 bits.
Even with QAT trying to manage them during training.
Even with QAT, they found some layers were still problematic. Specifically, they pointed to the input of the FC2 proj layer.
FC2 proj, why that one?
They used kurtosis, which measures sort of the peakiness and tailedness of a distribution. High kurtosis suggests more outliers.
And the FC2 input had high kurtosis.
Yeah. Figure 9A shows that even after QAT, that specific input tended to have higher kurtosis compared to other activations. It comes from the SWIGLU module, apparently.
Okay, so identifying a specific problem spot, what did they try to do about it?
They tried a mixed precision strategy. Since 8-bit quantization is often almost lossless,
Right.
they quantized just that tricky FC2 proj input to 8-bit, keeping everything else at W4A4. They called it XC2 input 8-bit.
Did that help?
It helped significantly. Figure 9b shows a substantial drop in the overall quantization error, especially for coarser granularities, like over 20% reduction for G32 and over 40% for G256.
Wow, so targeting that one input made a big difference.
It did. It also made the activation error much less sensitive to granularity.
And did it change that balance between weight and activation errors, that ratio R?
Yes, it did. With the 8-bit FC2 input, figure 8d shows that R hovered much closer to 1. The weight and activation errors became much more similar in magnitude.
So once you address that specific activation bottleneck.
The remaining weight and activation errors are more evenly matched.
Okay, so a practical point here is that maybe you need to treat certain activation layers differently, like this FC2 input, for really effective low-bit QAT.
That seems to be a strong suggestion from this work. Handling that FC2 input, maybe with mixed precision, seems key. And once you do that, improving W4A4 further might mean you need to focus on optimizing both weights and activations together, since they become more balanced contributors to the error.
Makes sense. Lastly, how did their scaling law compare to previous ones?
The main improvement they highlighted was incorporating granularity, G. Older laws often needed separate fits for different G values.
Right, you mentioned that.
Their unified law handles different G values within a single formula. Table 2 shows this leads to much lower prediction errors compared to prior approaches for both the W4A16 and W4A4 scenarios.
So including D helps accuracy, and modeling G makes it more adaptable.
That's the conclusion, yes.
Okay, let's wrap up. What are the core takeaways for listeners from this exploration of QAT scaling laws?
I'd say there are 3 main things. First, this unified law gives us a better handle on 4-bit QAT by linking error to model size, data volume, and granularity together. Second, activation quantization, especially around that FC2 layer input due to outliers, looks like a major bottleneck, but it can be substantially reduced using mixed precision.
Right, the 8-bit fix.
And third, once you tackle that main activation issue, getting even better W4A4 performance likely requires paying attention to both weight and activation quantization more equally.
Really useful insights. It definitely makes you think differently about how to approach building and optimizing these highly quantized models.